Hello, everyone. My name is Rohit, and I'd be performing experiments on MSP432 as per the CX6024 intermittent computing class. And my partner is also named Rohit. So both of us would be taking you through various experiments on this microcontroller. And so let's say we call this as, oh, sorry, the MSP432 series, wherein we go from basic programs, like we start from embedded Hello World, UART, and then we go up to benchmarking certain programs, testing cryptographic programs, and then seeing how much energy they're taking and so on. But that's for the later sessions. So today we would be focusing on embedded Hello World. So if we see for a software program, a usual Hello World program is just it just runs on your computer, and then you create a make file, or the compiler compiles it, and then you see a gleaming hello world on your computer. But in the embedded domain, it's just a microcontroller, so there's no way you can actually see hello world anywhere. I mean, there are ways with UART, but the most basic way on how we test a microcontroller is using a blinking program. That is, we just blink an LED, and if it's blinking correctly, then we can safely say that we have booted, or we have started our microcontroller. So before we jump into the code, let's have a brief overview about what the MSP432 is. And so the board has lots of features. And so we would just be focusing on the features which are essential for our experiment, or our code, because otherwise it's just too much theoretical data. So the most basic element of that is the Cortex M4 32-bit ARM processor, and that is around which the whole board is designed. And in today's program, we would be using one of the four counters. So, sorry, the timers. So there are two 32-bit timers and four 16-bit timers. And so for today's blinking thing, we would be using one of the 32-bit timers. We would be setting that, we would be configuring that, and we would be using the delay or the counting of that timer to generate our blinking program. So we would be using the driver lib.h library. This library has inbuilt APIs which control GPIOs, UARTs, timers, and stuff like that. So you can control them directly from your program rather than going on the register level and doing programming. And naturally, the environment wherein we do all of this is called Code Composer Studio, which is like quite a popular tool when it comes to programming Texas Instruments microcontrollers. So after this, let's jump in the code. So I'll start Code Composer. So usually what we do is I've like written a program here. Me and Rohit have written the program. So we usually go in projects, and then we import a CCS project, and then we browse. So you need the driver lib installed on your computer. Of course, you can go to new project and then make a new project, but then you have to include the driver lib, you have to include the location of where the driver lib is, and there's a lot of linker files that are involved in it. So better than all of that is you just go to the driver lib, um, which is, I mean, this is the driver lib library. It's in my workspace. It can be anywhere, to be honest, but this is your driver lib folder, which you get after downloading MSP432 driver libraries. And then you just go to examples, and then empty projects, and just import the first project. So I've already done that, so I won't be importing it again. But this is the easiest way in which you can get started with anything on MSP432. So Rohit, would you like to continue? Just a second, just a second. You may start. Yeah.
So yes, thank you, Rohit. So I'll walk through the code. So at first, can you scroll a little bit up?
Okay.
Yeah, thank you. So here we first include the driver lib, as Rohit explained very beautifully that what the driver lib is. And so we'll go ahead, and then these are the just standard input output libraries and standard bool library. So we define here the macros, which is the LED red LED pin, which is the GPIO pin 0 on the board. And then we also define the LED port, which is the GPIO port P2. And then we go ahead and um, describe the uh, integer, which is your int32 underscore t for LED state. And then these are the four functions which we'll be using in the code. And LED flash init is a function which will define the GPIOs for the LED Blinky. And then timer 32 init is a function where we are going to see how the timer is initialized and generated. And LED flash change state function is the function where all the blinking code is written for the changing of the state of the LEDs. And delay loop wait is a function which will generate the delay. So we dive into the int main void. So first we initialize the watchdog timer, and then we initialize the LED flash init and timer 32. So if you can scroll a little bit down, so I can explain these functions. Yes, thank you. So LED flash init void is a function where we are just defining the GPIO set as output pin. So this is a driver lib function. So it sets the pin as output. So first we define the LED1 port, and then we define the red LED1 pin. And then we also define the LED state G is equal to 0, which means that first we are putting the LED in off state, and the function next to it, which is the void timer 32 in it. So this function is just generating or emulating a delay of 50 milliseconds. So timer 32 underscore 1, which is a 16-bit timer. So it is just so the value 15,000 minus 1, which is 14,999, is been loaded into the timer 32, which means that uh, this value represents the number of clock cycles the timer will count before generating an interrupt or triggering a delay or emulating a delay. And then timer 32 underscore 1 control, we are setting the value of 0xC2, which indicates the specific control settings for triggering the timer interrupt. So yeah, Rohit will dive next into the code.
Sure. So now that we are done with initializing everything, while one is where our LED will keep on blinking continuously. So the first thing is change the state. So the state, we are keeping a track of the state with this variable LED state underscore G. And we have initialized it to 0. So it's a pretty straightforward function. Like if the state is 0, then make it 1 and then set output as high on the pin. And if it is 1, then set it to 0 and then set the output low on the pin. So we change its status first and then we do that physically on the pin. But the most interesting thing here is how do we generate that delay? So we have a timer which can generate a 50 millisecond delay, but we need to stretch it to 1 second. So we have the delay loop wait function. And what is this is doing is it's still controlling it with a for loop. So there's some software delay involved in it, but it's a combination of both software and hardware delays. And I'll say the most important line for this program is this one. So timer 32 underscore 1 is how we control the timer. So load and control were two APIs which we use to load the value and control the value. Similarly, RIS is like a flag which indicates if the timer has overflown or not. It's the raw interrupt flag. Don't exactly know the full form of it, but whenever the timer completes 50 milliseconds, the value of RIS becomes 1. And so what this while does is when the value of RIS is not 1, then 0 and 1 is 0. So 0 is equal to 0. So it just keeps on flowing in the while loop. And when your timer overflows, the value of RIS changes to 1. And that's when you jump out of the while loop. And that's how your 50 milliseconds are complete. And then you again put the timer, you clear the value of the timer, and then it resets to 0 because that's how we have put it in the timer control settings. So it does this 20 times. And so 50 milliseconds into 20 is 1 second. And that's how we generate that 1 second delay. And I mean, this was all the code. We debug this code um, with the hammer symbol at up top. I'll just do it again, and it usually shows any errors if there are. This code doesn't have any errors. And then this one's already running on my board. And if you want to run the board, you just do this bug symbol over here, the debug one. I'm just gonna press it again. Let's see what it does. So it flashes the board, and then you just need to press this play button as in songs. And then once you press this, your board starts running your program. So as you can see, there's the light that's blinking. So, to have like a closer look at it. Um, yeah, this is your light, and this is what it's blinking at 1 second. So this is how we do a simple blinking program. And so in the future videos, you'd be looking at how to use UART, and how we can test cryptographic programs on this microcontroller, and how we can actually measure how much energy was required for running these programs and so on. But this is the end of today's video, wherein we just did a simple blinking program. So I guess that's it on my part.
Yeah,
Thank
thank you.
you, and
And
thank you
thank you,
everyone.
everyone.
Thank you, everyone. Yep. So just stop recording.